Today's video is an introduction to angles. We've got three objectives. We're going to look at degree measures of angles, then radian measures, and finally reference angles. We start with the degree measure of angles, and a note: an angle is composed of two rays with a common endpoint, the vertex. The fixed ray is the initial side, so where it starts, and the rotated ray is the terminal side, so where it ends. Definition here: an angle is in standard position if its vertex is at the origin and its initial side lies on the positive x-axis. Definition: angles in standard position whose terminal sides lie on the x-axis or y-axis, such as angles with measures 90 degrees, 180 degrees, 270 degrees, and so on, are quadrantal angles. Right, and we can see the quadrants there again in the picture on the right. Quadrant 1, upper right, from 0 to 90 degrees. Quadrant 2, upper left, from 90 to 180 degrees. Quadrant 3, lower left, from 180 to 270 degrees. And Quadrant 4, the lower right, from 270 to 360 degrees. So our full circle, 360 degrees, halfway around 180, dividing that 360 into quarters gives us the 90 and 270, top and bottom. Definitions here for some angle types. An acute angle is one with measure less than 90 degrees. A right angle is one with measure equal to 90 degrees, and an obtuse angle is one with measure between 90 and 180 degrees. 180 degrees would be a straight angle. You might remember from geometry. There's a couple more, but these are the ones we'll use a lot for our triangles. Note here, the degree measure is positive if the rotation is counterclockwise. And negative if the rotation is clockwise. So that just follows from how we labeled the quadrants, right? Quadrant 1 was the upper right, then 2, 3, 4 as we move in the counterclockwise direction, so positively through the quadrants. And if we go clockwise, we'd be going backwards through those quadrants. Definition here: angles with measures 30 degrees and 390 degrees have the same initial side and the same terminal side, but different amounts of rotation. Such angles are called coterminal. Their measures differ by a multiple of 360 degrees. Right, so every time we go around the circle and come back to that same spot, we can have a new angle with the same initial side and same terminal side, but different amounts of rotation. And so as we label the angles here, the differences in the rotation will be drawn with an arrow. So we're going to draw each angle in standard position. We start with 30 degrees. So that's going to be just a third of the way through quadrant 1. And put a little arrow there to show our rotation counterclockwise for the positive angle. 105 degrees would take us slightly into quadrant 2 because it's more than 90 degrees. So we can mark an angle and show the rotation. For negative 220 degrees, we're also going to end up in quadrant 2. If we started 0 degrees over here and go in the negative direction, so clockwise, we'd get negative 90, and then negative 180 degrees. So a negative 270 if we want to see that third quadrant, so it would stop here about halfway through, and we can show our clockwise movement for that angle measure. And then for the 390 degrees, hopefully easy to subtract 360 from that in your head there. You can see 30 was also listed in that definition. So it should be in the same spot as the 30, but to show the extra rotation, we go one full circle and then that little bit extra to come back into quadrant 1. For 2, we want to find the angle of least positive measure that is coterminal with each given angle. So least positive measure just means within one time around that circle. So somewhere between 0 degrees for our angle theta and 360 degrees. So starting with 699 degrees for A, if coterminal angles differ by a multiple of 360, we just want to add or subtract 360 until we get somewhere within that 0 to 360 range. Since this is bigger than 360, we're going to subtract it once and see where we end up. With 339 degrees here, we're between 0 and 360. If we subtracted 360 again, we'd get a negative measure, so it wouldn't be positive here. So that's our least positive coterminal angle. For B, we start with minus 541 degrees. So now, since we're negative, we're going to add 360s to go around the circle, get back to the same spot, but move in the positive direction. Adding 360 here is really just us subtracting and keeping the sign of that bigger number, the negative. So I'm going to write down the 1, and 54 minus 36 is 18, so 181 degrees. But we keep the negative sign because we had more negative to start. And then we've got to add another 360. Right, one more time around, but really we're going to take 360 degrees, subtract the 181, and keep the sign of our bigger number, the positive here. So, I don't know, we can write it out and borrow. You can use a calculator. We get a 9 there and then a 17, so 179 degrees for our least positive coterminal angle there. And negative 181 degrees would also be coterminal, but we're not positive yet, so we've got to go around again. All right, we'll do a lot more work with radian measures, so that's our next step here. Note, in calculus and many scientific fields, radian measures yield simpler formulas and are easier to work with. They provide a direct correlation between an angle measure and the arc length, a distance. So we have a definition: a central angle is a positive angle whose vertex is at the center of a circle. So if we have a radius of a circle that is r, and the length of the arc subtended or intersected by the central angle, so right, those thick black lines coming out, that's the angle they'd intersect, by the central angle is also r, then the measure of the angle is 1 radian. Right, so if this distance out here is r, is the same distance as the radius, then the measure of that angle is what we call 1 radian. Note, an unmarked angle is understood to be measured in radians, so we need to use that degree symbol to specify degrees. We can draw a couple pictures here to help us convert between degrees and radians. For our circle, we talked about a whole circle being 360 degrees, but if we start with an angle at the origin and on that x-axis, we'd have a 0 degree angle just straight out there. Up to the first quadrantal angle, that was 90 degrees, 180 degrees halfway around, 270 degrees was 3/4 of the way, and then a whole circle is 360 degrees. You also might remember the circumference of a circle is 2 pi r, and we just talked about how for a central angle, right, 1 radian is an angle that intersects an arc of measure 1 radian. So really this is 2 pi radians. And so we know for a whole circle, all the way around, an angle, a central angle, would have measure 0 if we don't move at all, but 2 pi for the full circle. Right, so it's 2 pi radians to go all the way around. So halfway would be pi. Half of that is pi over 2, and then 3 pi over 2 at the bottom. So that whole circle, 360 degrees, is the same as 2 pi radians. Halfway around then, 180 degrees is the same as pi radians. And if we do divide those both by 180 degrees, we get one of our conversion factors. 1 degree is the same as pi over 180 degrees radians, or 1 radian is the same as 180 degrees over pi. All right, so we'll use those two to convert for us. We're going to convert each degree here to radians. For A, we've got 108 degrees. We're going to multiply by pi over 180 degrees. The easy way to think about this is with conversions, like you've done in hopefully other math classes, but chemistry a lot too. We're kind of dividing out units. So the 180 degrees on the bottom here gets rid of our degrees and turns this into a radian measure. We can divide both by 36, and we get 3 pi over 5 radians. For the negative 135 degrees in B, we're again multiplying by that pi over 180 to convert to radians. You'll get used to some of these values as we move into the unit circle. For now, trust they divide by 45. You can toss it in a calculator. Should reduce to minus 3 pi over 4. And for the 325 degrees in C, we're again multiplying by pi over 180 degrees. Those, I think, just divide by 5. So we get a 65 pi over 36. All right, and we're into radians again. We divide out those degrees, you can think, as we go. To go the other direction, to convert each radian measure to degrees, we are multiplying by 180 degrees over pi. So for the most part, that conversion idea, again, we're dividing out the pi's, and we're being left with degrees, because we only had 1 degree. The 180 divided by 5 gives us 36, times 3 should take us back to 108 degrees. So you can see the A is for both, we're just swapped. We're going back and forth. For B, we're multiplying by, again, the 180 degrees over pi to end up with degrees. 180 divided by 6 is 30, so times 7 gives us a negative 210 degrees. And for C, you'll need a calculator, but it's there just to show you these aren't all perfect. If we have negative 3 radians for a measure, we're multiplying by 180 degrees over pi. If you toss that in a calculator, we get approximately negative 171.9 degrees. All right, but we can multiply to go back or forth. Just divide by the thing you want to get rid of, the degree or the pi. For 5, we're finding 2 positive and 2 negative angles coterminal with minus pi over 3. So if 360 degrees was a whole circle, and that translated to 2 pi radians, then our coterminal angles are going to differ by 2 pi radians. And for us, since we're working with pi over 3's here, 2 pi over 1 is the same as 6 pi over 3. So we're just going to add or subtract 6 pi over 3 to move around the circle. We've got a minus pi over 3. I feel like I usually do positive first, so I'm going to add 6 pi over 3 to get one coterminal angle that's got a positive measure. That's 6 and negative 1. We'll add together to make a 5 pi over 3. And then we can take that 5 pi over 3 and add another 6 pi over 3, so another time around the circle, to get 11 pi over 3 for another positive coterminal angle. To get negative angles, we just want to go backwards, so minus pi over 3 minus 6 pi over 3, get us to a negative 7 pi over 3. And if we take that negative 7 pi over 3 and subtract another 6 pi over 3, so another time around the circle in that clockwise direction, we get a negative 13 pi over 3. So those 4, 2 positive and 2 negative coterminal angles. But again, just going a one time around the circle so we get back to the same ending point. And we can add or subtract 2 pi to do that for radians. The last objective is reference angles. We start with a definition. A reference angle for an angle theta, written theta prime, is the positive acute angle made by the terminal side of an angle theta and the x-axis. We're going to draw a lot of pictures in the trig portion of this class, or drawing a lot of pictures will help you out at least. So we want to get used to drawing these reference angles and what we'll call reference triangles a little later on. We can start by labeling our quadrants, right? Quadrant 1, that upper right, quadrant 2, upper left, quadrant 3, lower left, and quadrant 4, lower right. We can label the angles as well. So 0 degrees down here is the same as 0 radians. Up top, we'd have 90 degrees or pi over 2 radians. On the left side, 180 degrees or pi radians. And down at the bottom, 270 degrees or 3 pi over 2 radians. And if we complete the whole circle, again, that was back to 360 degrees or 2 pi radians. So I'll write these out in degrees. We'll do problems with both. But in quadrant 1, so I'll draw kind of a magnified view of quadrant 1. Our acute angle is already somewhere between 0 and 90, so theta is the same as theta prime, right? We'd already have an acute angle there if it just rotates into quadrant 1, so whatever the angle measure is our reference angle. And we'll get used to thinking about a lot of things in terms of an angle in quadrant 1. Quadrant 2, we're somewhere between 90 degrees and 180 degrees. So if we have an angle over there in quadrant 2, right, with our rotation from that angle in standard position, that would be our angle theta. And so really we just want to find the difference. What's that leftover piece? What's that acute angle that is theta prime? And here we can get the one for most positive angle measures by taking degree there, the 180 degrees minus theta, right? That would give us that leftover. In quadrant 3, we're somewhere between 180 degrees and 270 degrees. If we have our rotation here to give us angle theta, we can see that theta is bigger than 180 degrees. We want to subtract off the 180 to get that leftover theta prime in the middle. So we can think theta here minus 180 degrees would give us that leftover theta prime. Right, and again, it's just a subtraction just to figure out where our angle resides or where it lives. And if we were dealing with something in quadrant 4, where we're between that 270 degrees and 360 degrees, our rotation would take us all the way to quadrant 4. That's theta. Theta prime is just that leftover bit, so you can see it's a little bit less than 360. So we can usually use some subtraction there. 360 degrees minus theta would give us the leftover bit, theta prime, that would complete the whole circle. All right, so we'll try a couple to finish off the section. Draw each angle in standard position and determine its reference angle. And I gave some weirder ones here, I hope, but we'll just think about where they live and what that little leftover bit is. So negative 225 degrees takes us past that negative 180 degrees we drew for a problem earlier and into quadrant 2 over here. Really, it's going to be exactly halfway through. So this is our theta, our negative 225 degrees, and we want that little leftover bit, theta prime. So for us here, the difference between 180 and 225 is just 45 degrees. So that's going to be our theta prime, right, our reference angle. Right, positive acute angle, so even if we subtracted the negative 225 minus negative 180 or something, we still want to make sure that angle measures positive. For 5 pi over 3, we'll talk more and you'll get used to where the radian measures reside as we move through the course, but that's going to put us in quadrant 4. Right, this would be our theta coming around. We want theta prime, that little leftover. We're in quadrant 4, so you can think subtracting from the whole circle. That'd be 2 pi in radian measures. So 2 pi, or we said that was the same as 6 pi over 3 for our coterminal angles above, minus the 5 pi over 3 gives us a theta prime here of just 1 pi over 3. And for the last one, C, 17 pi over 6. We know 2 pi, again, is a full circle. That's the same as 12 pi over 6. So 12 pi over 6 would be us going all the way around, coming back to the beginning. And 18 pi over 6 then would put us halfway around again, another pi, another 6 pi over 6. So 17 pi over 6 is going to go all the way around, come back into quadrant 2, right, a full circle and then back. That's our theta. But really, we just want to know that leftover bit. So I did some of the scratch work there on the side. We got 18 pi over 6. Would be the same as 3 pi, right? So 2 pi bigger than pi over there. And the 18 minus 17 gives us just a pi over 6 remaining for that little reference angle theta prime. All right, most you work with I think will be a little easier than that, but just to get used to this idea of that coterminal, we can go around more if we need to. And the reference angle is always just that leftover acute angle between the terminal side and the x-axis. That's the important bit. So complete the ticket in the door, and I'll see you in the next one.